Hello world and hello maths fans. Today we are talking about graphs. Once we have translated a real-world problem into the language of maths using variables and equations, we then want to visualize those relationships, and that is exactly why we need graphs. We'll begin by looking at the Cartesian plane, the grid-like system which we use to plot points and then construct graphs. We'll then look at some of the simplest graphs in the form of linear or straight line graphs and define the terms gradient and intercept. We'll then move on to more advanced graphs in the form of non-linear graphs such as quadratics, polynomials, exponentials, and logarithms. We'll then compare all of those graphs and see what they look like together on the same axes. And finally, we'll end with a demonstration of different growth rates. That's not what we end on. We end on rubber ducks. Hello world and hello maths fans. Today we are talking about graphs. Once we have translated a problem into the language of mathematics through equations and variables, we then want to visualize that problem to see if we can identify any relationships and trends, and that is why we need graphs. We'll begin by defining the Cartesian plane, which is the grid-like system that we use to plot points and then draw our graphs. We'll look at some of the simplest graphs in the form of linear or straight line graphs and define terms such as gradient and intercept. We'll move on to more advanced graphs in the form of quadratics, polynomials, exponentials, and logarithms, and we'll compare their growth rates with a brief introduction to the concept of a limit. We will end with a demonstration of the graph of the breeding patterns of rubber ducks. But first, I've got some treasure to find. Hello world and hello maths fans. Today we are talking about graphs. Once we have translated a real-world problem into the language of mathematics through equations and variables, we then might want to visualize those relationships to help us to identify any patterns. And this is why we need graphs. We'll begin by defining the Cartesian plane, the grid-like structure that allows us to plot points and draw our graphs. We'll look at some of the simplest graphs in the form of linear or straight line graphs, before moving on to more advanced graphs in the form of quadratics, polynomials, exponentials, and logarithms. We'll then compare those graphs with an introduction to limits in the form of a comparison of growth rates. Finally, we will end with a demonstration of a graph of the breeding patterns of rubber ducks. But first, I've got some treasure to find. Here, I have a treasure map. But it's not just any old treasure map. This is a mathematical treasure map with very precise instructions using what appear to be some kind of coordinate system to guide me to my loot. So I'm going to try and see if I can follow these instructions and uncover the location of the treasure and dig and find some jewels. Let's give this a go. So first of all, it gives me some instructions about how to use the map. And it mentions that I want to begin at the center, which is the swamp. So I'm going to find the center. This looks like a swamp to me. So I'm going to position myself nice and in the center. And it says that I should call this 0, 0. OK. Now, it informs me that there are two important directions. It says that moving horizontally in this direction is going to be the x direction, and moving vertically in this direction is going to be the y direction. Right, so I think I probably now can follow the first instruction. It says 3 steps in the positive x direction. So we said this direction was x, horizontal was x, and it wants me to take 3 steps in the positive to the right direction. So let's go 1, let's go 2, and 3. OK, so I should now be at 3, 0, which makes sense to me. If I started at 0, 0, and then I've added 3 to that first coordinate, then I am now at 3, 0. OK, I think so far so good. Next, it suggests, or tells me, in fact, that I should take 2 steps in the negative y direction. So if this one was the positive y direction, then negative y means I'm going down the map. OK, so 2 steps, negative y. 1 and 2. OK. Oh, and it says I should arrive at a palm tree. OK, I seem to have arrived at the palm tree. So this is good. OK, it says now, well, there's a lot going on here. It says now I want to look for a second palm tree. OK, so there's another palm tree over there. Right, so it's telling me now to walk towards the second palm tree. OK, and it very helpfully says this should be the negative x direction. So let's just make sure that makes sense. So if I turn myself towards the second palm tree, so if I went that way was positive x, then I think this way is going to be the negative x direction. This looks good, and it says to walk towards that palm tree. OK, 1, 2, 3, 4, and 5. OK, so I've reached that second palm tree now, and it says at this point I should be at the position -2, -2. OK, I'm just going to see if that makes sense. So I started in the middle, I went across 3, I went to 3, 0. I then went down 2, which took me to 3, -2, and then I've come across. So I'm still on -2 in that vertical direction, but I've now gone in the negative x direction, and I went 5 steps. 3 - 5 gives me that -2. OK, I think I am at the right tree. This seems to be -2, -2. Right, next is going to say positive y direction, 4 steps. OK, so that's going to be up. That's going to be 1, 2, 3, 4. OK, there's nothing in the landscape to help me, but I think this is correct. Oh, it does say -2, 2. So before I was at -2, -2 at the palm tree, and now I've gone 4 in the positive y or vertical direction, so that makes sense. I'm now at I'm at -2, 2. OK, so still negative x, but now we're at positive y. OK, nearly there. Says there's a bridge. I can see a bridge. Says I should cross the bridge, or use the bridge to cross the river. Right, well, let's do that. So 1, 2 on the bridge, and I've successfully crossed the river. And then 1 more step, and it now says I should be at the position 2, 2. So I was at -2, 2, and I've just moved a total of 4 steps in the horizontal positive x direction. So I think this is 2, 2. This looks good. And And then finally, it says 1 step in the positive y direction to the position 2, 3. And I believe this should be where the treasure is. Okay, right, well, let's give this a go. So I think it's this spot here. X marks the spot. Let's see. Haha! Treasure! Success! My mathematical treasure map has led me to the loot. All right, now let's just take stock of everything we've seen there. There was a lot of maths and terminology introduced in that treasure hunt, so let's make sure we're happy with everything we've just seen. So the grid that I was moving around on there, following on my map, is called the Cartesian plane. So the Cartesian plane, as shown here, so we've got the axes in white going from -2, -1, 0, up to 5 horizontally, and then vertically also from -2 up to 5 as well. And then we've got the grid lines shown in blue. Now, we call the horizontal axis the x-axis. So again, this extends in the negative direction and extends in the positive direction, and each mark, each grid space, is increasing with those integers. And then vertically, we call this axis the y-axis, or the y direction. So we have positive y direction going up the page as I was following with my map, and then down we're going in the negative y direction. The place where I began, my origin, as it were, for the treasure hunt, is 0, 0. And this is a common term used when looking at the Cartesian plane. And then in terms of where the treasure was, so as I was following the map, there were various coordinates helping me on my way. And those coordinates are just the x coordinate is the first entry. So we would write x, comma, y, where the second coordinate is the y value. So where the treasure was found was the location 2, 3. So what that's saying is ultimately the treasure was at 2 spaces along the x, or the horizontal axis, and then we went 3 spaces up to get to the y coordinate. It would have been much easier if my map had just given me those values. I could have gone straight there. But of course, pirates being pirates, they had to send me around the houses. let's look at how we can construct linear or straight line graphs by plotting points. Our starting point is going to be the Cartesian plane, the grid-like structure that labels the x values horizontally and the y values vertically. Now, if we want to try and build or construct a graph, one way to do this is, given certain data, given values for x and y, is to plot those points on our grid system and then join them up. So let's have a look at an example. So here we have values for x in the first column, remember our horizontal value, and then we have values for y in the second column, is going to be the vertical value. And we're just going to go through these as a pair. So when x is 1, this tells us that y is also equal to 1. So we just go across to our Cartesian plane, we go 1 across for x, 1 up for y, and we put a dot to represent that first point. We do the same again. So again, we've got now 2 and 2, so we go across 2, and we go up 2, and we draw our second point. The next one says go across 3 in the x direction and up 3, so we mark that point there at 3, 3. And then finally, we've got 4, 4, which is going to be up in that top corner. And the dot, dot, dot here is just telling us that this pattern is going to continue. So I could keep adding more and more points following the same pattern that we're seeing in the table. But at this stage, I think we have enough information to see what this linear graph is going to be. So we can join all of these points up with our straight line to get our straight line graph, our linear graph. Now, when we look at this graph, there's a couple of important things to be aware of. So one of them is that this is what we call a positive slope or a positive gradient. And that's because if we look at the x and y values, sort of as we increase x by 1, shown here by this horizontal dotted line, we move 1 horizontally, the graph is then increasing vertically also by 1. So since both values have the same sign, that's telling us this has a positive slope, so going from left to right, as shown on the screen. And we've also got here a bit of a clue about how steep that slope might be. So for example, this one has a slope of 1, more on that in a moment, but you could imagine having something a bit steeper or a bit flatter, and that steepness is going to be how we refer to the slope or the gradient. So let's look at another example, and again, we'll construct it in a similar way with some data points. So cleared the graph, and now we have a different set of data. But again, we've got the x value, the y value. We're just going to draw those, plot those points as a pair. So x is -2, y is 4. So we've got some negative values now. So we go to -2 on the x-axis horizontally. We go up 4. It's going to be up here, and we draw our first point. Then we go 0 and 3. So again, 0 along the x-axis tells us to move up here to 3. We add in that point. Continuing, we then go to 2, 2, across 2, up 2, gives us that third point. 4 and 1, across 4, up 1, gives us that fourth point. And again, this is telling us the pattern continues, so we just extrapolate the data in both directions. OK, so now if we draw our straight line through this one, again, we've got a lovely straight line through all those points. This is still a linear graph. But we're seeing a different slope, so it's pointing the other way, and this is the negative slope or the negative gradient. And we can see that very explicitly if we do a similar trick by looking at that triangle below the line. So if we draw in what's happening horizontally and vertically, then we see that as y is decreasing, we're going down in the y direction, and then we're going across 2 in the x direction. So they have opposite signs, and that's what's telling us that overall we have this negative gradient. We're also seeing here a different property of the slope or the gradient. So if you think back to the one we had, this one is less steep. So ignoring positive or negative, this is going a more gentle slope. And that is being seen here by the fact that the x and the y changes have different values. So we've learned a couple of important things. We're seeing that we can have the sign of our slope can change, positive or negative, and gives you a different graph. And we're also seeing that the steepness, like how sharp is that slope, is it quite steep or quite gentle, is also changing, or the magnitude of the slope or the gradient is also changing. So it's probably time we define what is happening through the form of an equation. So for both, nope, I've got that bit to do first. Should I just say the last line? It's probably time, no, because that was the wrong last line. So I just said we've seen that the slope has two different properties. Okay, I'm just going to go from there. So I was here, and I just said, so we've seen that the slope, forgot I've got to do the other side. Okay, so we've seen the slope has two different properties. Okay, I'll just read it a bit. So we've seen, so in these examples, we've seen there a couple of important properties about the slope or the gradient that can change. So we've seen that it can be positive or negative, pointing from left to right for positive, no, pointing from bottom to top. Okay. Try that one again. So we've seen, okay, so in our examples. So in these examples, we've seen a couple of different properties that we can observe with the slope. So we've seen that sometimes it can be positive, going from low down here up towards the top right corner, and here we've got a negative slope or a negative gradient. So we've seen that the sign is affecting the slope. And we've also seen that the steepness can change. So sometimes it can be quite steep, or it can be more gentle. So we're going to see that the sign and the magnitude of the slope can both change. Now there is a final thing that I just want to point out on this graph before we define our equations for straight line graphs. And that is how I have drawn on this triangle. Because some of you might be thinking, well, the way Tom has done this has a negative value here. The y value, I've decided to draw down from y. But I could have equally decided to draw up from that point, and now y is going up by 1. And whilst y goes up by 1, x is decreasing by 2. And you'll notice, whilst the numbers have swapped signs, they still have opposite signs, which is telling us it still has that negative gradient. So both of these are equally valid ways to think about the slope or the gradient. OK, now onto that equation. So a linear graph, the general equation for a linear graph, the two examples we've seen, has the form y equals m times x plus c. This is sometimes referred to with a different letter, can be y equals mx plus b, you may have heard of, where m is the gradient or the slope. So the number in front of x is telling you about that slope, positive, negative, how steep it is, and c is the intercept with the y-axis, so the point where your graph crosses the y-axis. The gradient specifically is calculated m equals rise over run. This is a very helpful way to remember what is happening. So rise, it's a colloquial term. Rise means the change in the y coordinate. So up or down is the rise. You're rising up or rising down. And then in the x coordinate, the change there we call the run, as you're sort of running forwards or running backwards. So you're moving horizontally when you run, and when you rise, you're moving vertically. So it's a very helpful way to remember how to calculate the specific slope or gradient. So now let's do this for those two graphs that we've just seen. So we go back to our first graph. So this one we know has a positive gradient. We'd already identified that by thinking about what was happening. And if I add back in these values, we go 1 across and 1 up. So our formula for the gradient, m, is equal to the rise, so the change in y, which is 1, divided by the run, the change in x. So it's simply y equals 1 over 1 times x. And then the intercept is going to be where this crosses the y-axis. And as we can see, it's going through the point y equals 0. So plugging that into our general formula down here, we say y is equal to rise over run times x plus 0. Now, of course, we can simplify this quite a bit. In this example, 1 divided by 1 is just 1. And usually we don't write the 1 in front of the x. And because we're just adding 0, again, we generally don't write plus 0. But this shows you very explicitly where the m and c values come from. So this is just, of course, the graph y equals x. And I'm sure some of you spotted that by just looking at the values in the table. Now, for our negative gradient example, we can follow the same kind of pattern, same idea. So if we add our triangle, and again, I'll just first of all do this from below the line like so. So the rise here is negative, and that's fine. It's still the change in the y direction. so it's minus 1. And then we divide by the run, and the run here, in change in x, is positive 2. So writing that in our formula, we're going to get y equals minus 1 divided by 2 times x. And then we have to remember our intercept, and we can see here it crosses the y-axis at 3. So we've got our plus 3, representing that constant c or b at the end. So y equals minus 1 divided by 2x plus 3. Again, we just tidy that up a little bit and often write this as minus x over 2 plus 3, just to make it look a little neater. But remember I said I could have switched this and drawn the lines on this side, right? And I claimed we should get the same answer, so we should really check that that's going to hold. So if instead I had measured it this way to look at the slope, the rise now is 1. So the change in the y is 1. We're going up 1. But now the change in x is negative. So the run is minus 2. So the gradient m is rise over run. So it's going to be 1 divided by minus 2. So we can plug that into our formula. The intercept, of course, hasn't changed at all. And now if we tidy this up, 1 divided by minus 2, it's still negative a half. So we still end up with minus x over 2 plus 3. So it kind of shows us it really doesn't matter on which side of the line you're drawing that triangle to work out the rise and the run and to get your gradient. So to summarize, for a straight line graph, we need to look at the gradient, the slope. It can be positive or negative, and we can work out its magnitude using the formula m gradient equals rise over run. And don't forget to add that intercept plus b or plus c to get your final equation, y equals mx plus c. whilst linear graphs are incredibly helpful, a lot of real-world data doesn't have that nice straight line shape. So I'm going to share with you some of my favorite examples of real-world data where there is a need for a different type of graph, a different shaped graph, in order to match what we're seeing from that data set. So the first example is a lovely one. Two graphs shown on screen display the same information. So we've got here the speed of an animal going up the y-axis vertically, and then we've got the mass of the animal across the x-axis. And this is taken from a real piece of academic research. And what the researchers have shown here is that as the animal's size increases, so as you move along the x-axis, both for creatures that live on the land and creatures that live in the water, as you increase the size, we're seeing that the top speed of that animal increases. So bigger animals move faster. A lion is faster than a mouse, for example. So bigger animals move faster. But that would be a nice straight line relationship, except if you get too large. So if you sort of go from like lion, cheetah size right through to an elephant, right? A cheetah is going to beat an elephant. So the relationship doesn't continue. So we're seeing that whilst it's sort of a straight line to begin with, it then dips and comes back. So we have something here called a turning point in the graph. We have like this hump shape. So this is not going to be a straight line graph. So we're going to need something else. And we see the same over here going through to the sailfish, one of the fastest creatures in the ocean, through to something like a blue whale. You get so big, you start to come back down. So to capture shapes like this, these hump or N-shaped graphs, we need something else. And what we need is a quadratic graph. So a quadratic equation, a quadratic graph, looks like y is equal to a times x squared plus bx plus c. So a, b, and c are our constants. X is still the horizontal axis and y the vertical axis. And the key thing here compared to our linear graphs is we have the squared term being added in. So with that squared term, it means we end up with two now very distinct shapes that are no longer a straight line. So when a is positive, when this first coefficient on the x squared is positive, we get a U shape, so something like this. And then when you flip that and you make a negative, it flips the graph. So when the coefficient in front of your x squared term is negative, you get the hump shape or the N-shaped graph. And this is what we're seeing with this model for animal speed limits. Now, the second example I wanted to share, also from a piece of academic research. Nope. OK. Right, so I'll just go from here again. So this is what we see. So we've got this shaped, we've got this hump shape or this N shape. OK, we've got this hump shape or this N. OK, instead A is OK. So when A is negative, we get that hump or that N shape, and that's exactly what we're seeing here with these graphs for the animal speed limits. Now, this type of graph, this quadratic graph, is actually a subset, a smaller part of a much larger collection of graphs, which we call the polynomials. So the prefix here, poly, is saying many, just like dec in decimal is telling us 10. So an equation for a polynomial, generally speaking, is some coefficient multiplied by x to some power. And then you just keep adding. So we would go an times x to some power n. And the next one would be x to the n minus 1. And you just keep adding all of those smaller and smaller powers of x all the way down to a single x and then a constant at the end. And the quadratic that we've just seen is exactly what we get when this n is equal to 2. So that's telling us that the largest power of x is 2. And then we get our quadratic equation, constant times x squared plus constant times x plus constant. And if we then increase it to n equals 3, this is another very helpful graph shape to be aware of and be able to spot, we get the cubic equation. So the cubic equation, the cubic polynomial, just means we now have an x cubed. So we just go up to the next power of x. And we can keep doing this. You go cubic to quadric, quintic, etc. You're just increasing the power of x. But the cubic shape is a really interesting one. So for the quadratic, we saw that U shape or the hump shape. But for the cubic, we get this kind of fun S shape coming down, and that's because it has an odd power. So the cubic can be very helpful when you need something that's a bit different to the U or the hump shape. OK, so that's quadratics, polynomials that helped us look at animal speed limits. Now, I have another favorite graph that I'd like to share with you all, which doesn't fit into one of these polynomial shapes, one of these polynomial graphs. So this, nope, I keep going to that bit too soon. Let me just quickly check the order so I don't do that again. Sorry. So we've got the cubic, the quadratic. There are other polynomial graphs. So let's kind of compare them all now and see what they look like together, because there are different shapes and different things happening as we change this highest power of x, right? What the largest power of x is in our equation. So if we begin with something pretty straightforward, something pretty simple, our linear graph. So this has x to the power 1. Then here, that is just going to be the pink line at the bottom. So that's our straight line relationship. Y is equal to x. It's a linear function. And then as we move through the nonlinear polynomials that we've just introduced, we go up to the quadratic in the form of the x squared. We go up to the cubic here shown in blue. And then we can keep increasing. And what you're seeing here is as we increase the power of x, these graphs are actually getting steeper and steeper. They're increasing at a faster rate. So the one I've shown here at the end is actually y equals x to the power 8, going all the way up to that 8th power. So for large values of x, we see them all increasing and spreading out. They have faster growth rates. Whilst for smaller values, they're all kind of the same, and they even intercept. But for long-term problems, or maybe if you're working with algorithms and termination times, you want to be thinking about this long-term behavior. And as we can see here, increasing the power of your polynomial, we see that the graph just gets steeper and steeper. OK, so it's probably enough on polynomials, and it helped us to understand the graph showing the speed limits of animals. So now I want to share with you my second favorite graph, which looks at the marathon world record for women. So again, this is taken from a real piece of academic research. We've got the reference for you on the slide in the description. And you can see here we've got the marathon time, the world record time on the vertical y-axis, and then we've got the year progressing towards the present day. And then we've got all of these data points and various lines trying to track what's happening. But the important thing here is we're seeing a decrease. We are getting faster over time. Women are running faster and faster when they're doing their marathons. But eventually, it's kind of flattening off, right? We can't keep going faster forever. There is this kind of flattening off behavior. There's like a limit to how fast a woman can run a marathon, or a human even can run a marathon. So we get this different type of behavior. And again, this now is actually no longer going to be captured by a polynomial function. We need a different type of function to track this decrease and flattening off behavior. And the type of function we need is something called an exponential. So an exponential graph has a general equation which is given by y equals a to the power of b times x, and then we add on a constant c at the end. Now we've got a few things happening there, a, b, and c, so let's see what they all mean. So the constant a we call the base. So that's the number a that we're taking to the power x. So as x increases, we are taking higher and higher powers of that number a. You know, a could be 2, and then if we increase x, we're taking higher and higher powers of 2, multiplying it by itself more and more times. We have the constant c. Now this actually will determine the minimum value. So that's going to be the flattening off section, which would be helpful perhaps for trying to predict that future world record. And we also have the constant b. Now b is inside the power alongside a, so we've got b multiplied by x. And the most interesting thing about b is its sign. So if b is positive, if we have like a positive number in front of the x in the power, then we get what we call exponential growth, and b is giving us that growth rate. But if b is negative, then we get exponential decay. We get a declining graph. So examples of what they might look like: if b is positive, we've got growth. We can see this is increasing as x goes to the right along that horizontal axis. And here we can see we're decreasing towards that minimum value as x is increasing. So again, this is going to be our positive b, and this is going to be the negative b. So if we go back to our world record graph, we can see very much this is now an exponentially decreasing graph. It's got that shape. It's flattening off. And so that's telling us that the b value here is definitely negative to get that decrease. Now we've talked about exponentials, I can introduce to you a couple of other interesting functions. And the first one is something called a logarithm, or log for short. So the logarithm is the inverse of the exponential function. So the exponential function takes you forwards, then the logarithm is the inverse. It takes it back. It undoes that exponentiation process. And the way you get the graph of this is actually very clever. So you take the graph of the exponential function, the one we've just seen, and then you draw the line y equals x, our straight line relationship through the origin, and then you just reflect across that line. So we have here our straight line, y equals x. We have an exponential function, simple one, y equals a to the power x, and we just reflect. Imagine putting a mirror along y equals x, reflect across that line, and that now gives us the logarithm graph. So because this function I've drawn is base a, it's y equals a to the power x, then we say the logarithm is log base a of x. So again, it's important to track what our base is in both situations, but the log is just the inverse of the exponential, and so we find its graph by reflecting in that axis. And then we can use this trick again for the square root function. So the x squared function, the squaring operator. So the square root is just its inverse, so going backwards. So if going forwards means squaring the number, we go backwards by taking the square root. And again, because we know the graph of y equals x squared, it's one of those quadratics, we can just reflect to get the graph of the inverse, the square root function. So we draw here in blue x squared, and then we've got our line y equals x. This was a little bit trickier to reflect because of this intersection point. But again, imagine putting a mirror along the pink line along y equals x, that straight line, and then reflecting the graph. That will give us the graph of the square root function, which is another helpful one to be able to identify and a helpful shape when it comes to matching with data points. Okay, so we've talked about a whole range of different graphs. So I'd just like to end by comparing them all and looking at what they all look like on the same set of axes, so on the same Cartesian plane. So we begin with our single straight line linear graph, y is equal to x. If we then add on our quadratic, so we saw that for the example of the animal speed limits, right, they're not a straight line, there's some kind of turning point behavior happening, there's a change happening, so we need something that curves. So that gave us the quadratic formulas, the quadratic graphs. And then we just saw that from the quadratic going up like this, we can then reflect to get the square root. So again, we've got the linear, the quadratic, and then the square root below the straight line. And then we also had the exponential. So again, here I've done base 2. So this is now plotting powers of 2 as they increase. And we see the exponential is just shooting off much, much faster than all of these others. The exponential has gone off the page, whilst all the others are still down here for a fixed value of x. And then from the exponential, we then reflected in the straight line y equals x to get the logarithm, which is down the bottom. So we can see here there are various different shapes to these graphs. These are things that are helpful to be able to identify, especially when working with data and trying to uncover what kind of pattern or relationship might exist in that data, like we've seen with animal speed limits or marathon world records. And also, this gives us a little bit of an insight into how all of these different functions behave, because each function here is representing a growth rate or a change with increasing x. And this plot is telling us that as we move through these functions, we're seeing a faster increase or a faster growth rate. Once we've defined several different types of graph, we can then begin to compare them and their properties by plotting them all. Sorry, I don't know why I paused. Try that again. Once we have several different types of graph, we can compare them and their properties by plotting them on the same axes. So let's take a look at how these different graphs behave when compared to one another. So if we begin with a plot showing 5 different graphs, and we begin by labeling the simplest one we can identify there, the straight line linear graph y equals x right through the middle. Now, the next, let's say, most complex or least most complex graph from this would be the quadratic going through those. No, it wouldn't. Take that from the top, sorry. OK. I need my intro. Oh, give me a sec. Once we have several different types of graph, we can compare how they behave by plotting them all on the same set of axes. So let's do just that. So here we have 5 different graphs. I'm going to identify them one by one and look at what that means about their growth rate. So when we're talking about growth rate, what we're thinking here is as we increase x, as we move along the horizontal axis, how does the graph respond? How quickly does the graph grow? We're changing our input. How quickly does that output, the y value, change? So if we look at the simplest relationship, y is equal to x, our linear graph shown right through the middle there in pink. So this is linear, so we'll put that in the middle as like the base of what we can use for our comparison. Now, the one in blue is a quadratic graph. And the quadratic graphs are a subset of the more general polynomials. So this is any function or any graph that has a power of x. So here we've got the quadratic x squared. And we can see that this is increasing much faster. For large values of x, it's increasing much faster than the linear one. And that's shown by the fact that it's above that straight line graph. So we can say that the quadratic and in general the polynomials actually have a larger or a faster growth rate than those linear graphs. So then if we take our quadratic and we then reflect it in the line y equals x, we get the square root, or more generally the roots. That is the subset of graphs we have here. And this one we can see is now increasing quite slowly. So as x increases, the y value is not going up that much. So this has a much lower growth rate. So that's definitely below linear. So the roots, to sort of describe that entire subset, square roots, cube roots, other powers, the roots as a collection of functions are actually going to grow smaller than the linear ones. Now, we've got a couple of others here. This one in light blue is going to be the exponential, the exponentiation function, exponential graph. Here I've taken the base to be 2. Remember, this can be any number. So we've got a 2 to the x. We can see this is shooting up incredibly quickly, and it's above all of the others. So if I were to kind of draw a horizontal line here, we can see all of these are still hanging out in low y values, but the exponential is shooting off the page. So that is increasing at an incredibly fast rate. So it's above the polynomials. So we put the exponentials over here. And just to reiterate, what we're comparing at the bottom here is this difference in growth rate. And then our final function, the one in orange, is the logarithm. So this is just the reflection of the exponential in the line y equals x, because it's the inverse of the exponential. So we get our log function down the bottom. So this is log base 2, because our exponential has base 2. And we can see that whilst the exponential increases really, really quickly, because the log is its inverse, it's actually going to do the exact opposite. So it's going to increase incredibly slowly. And we see that by this orange line being below all of the others. So the logs are going to go down here. And so what we've got here at the bottom of the screen is a very helpful sort of general rule to remember when it comes to growth rates. And this is telling you the order of terms or the order of limits. So as your input, your x value increases, as x gets larger and larger, then this is telling you how these types of function or these graphs will grow. So logs are the slowest, the smallest growth rate. Then roots go a bit faster as we move up to the square root. Then we move up to the linear functions. Then we move up to the polynomials. And finally, we have the exponentials, are the fastest growing type of function that we see here on the screen. So with this in mind, we can now ask some interesting questions and compare different functions. So I'm going to do that over at the board. So for our first example, let's look at a ratio of two functions. So let's suppose I have the function, let's call it y1, is going to be e to the x divided by x squared. Okay, so there's quite a lot going on here, but we're just trying to interpret like how quickly this grows, and will this grow to infinity, or will this shrink to 0? So we want to think about what happens for large x. So if we increase x, where does this function go? Does it keep going up, or does it go down? And the way we do that is by just thinking about that order of terms, those order of limits. So what we've got here, if we sort of say, well, y1 is really just, and I'm going to just use that squiggly line to say it's kind of what, generally what's happening here. We've got an exponential, which we know increases very quickly, and we're dividing by, it's very explicitly a quadratic, but generally speaking, it's a polynomial. So we've got an exponential over a polynomial. So as x gets larger and larger and larger, if we look at our order of growth rates, the exponential is going to win, right? So both of them are going to increase to infinity. Both the exponential and the polynomials, they both shoot off. As x gets bigger, so too do both of those graphs and functions. But the exponential increases faster. So because it's on the top and increases faster, it's going to win. So this function, we can say y1 will actually tend to infinity as x goes to infinity. The exponential wins out because it has that faster growth rate. So now let's look at a second example. So let's look at a function y2. And this time, let's suppose we have the square root of x divided by x squared. So again, we've got the same denominator. The x squared function is a type of polynomial. So let's say this looks approximately like something that's a root divided by a polynomial. And now if we look at our order of terms list, our list of growth rates, we see that the polynomial is increasing faster than the root. So here the bottom term wins out. So the bottom will always be bigger than the top. So this function is actually altogether going to decay to 0. So again, the root itself will go to infinity, polynomial goes to infinity, but the polynomial goes there much faster. It has a faster growth rate. So overall, the whole thing is declining, decaying, and goes to 0 as x gets larger and larger. Okay, another example. So this is now going to be a combination of terms. So let's suppose we have an exponential plus a log. Let's suppose it's log base 2 of x. I'm just going to pause because I've realized I've written e to the x throughout, and I've not mentioned that yet. Have I, David? So now we have an idea about how to compare functions. Let's look at some examples over on the board. So suppose we are comparing two types of function. And let's say the first one is 2 to the x. And we're interested in 2 to the x versus a different function. And let's say this is x squared. So we know that as x increases, we know the exponential function 2 to the x increases as well. That will go all the way to infinity as we keep increasing x. And so will x squared. But we now have an idea about how fast they go towards infinity. So when we're asking the question of which one is going to increase the fastest or which one wins, thinking of it as like a race between the two, then a helpful way to do it is to consider their ratio. So you kind of think about having one function divided by the other. So if we set that up and say, let's look at 2 to the x divided by x squared. And now, as we increase x, they both get bigger and bigger and bigger. But we know that the top is going to increase faster. So what we've got here is we've got an exponential function on the top, an exponential graph that's exploding at this incredibly fast speed divided by a polynomial. And once we've kind of rewritten it in these terms, we can now look at our order of terms, our order of limits of those different graphs, different functions, and we see that the exponential is going to beat the polynomial. So that means that this will then go, this ratio will reach infinity. So we can kind of get a bit of an idea of what's going on with limits through this process. So we can say something like, if I have the function y1 is equal to 2 to the x over x squared, then what we've shown here, or by thinking about growth rates, is the limit of this function as x goes to infinity. We've shown that that is equal to infinity. And that's just because the term on the top beats the term on the bottom. Now, if we look at a slightly different comparison, different ratio of these functions, maybe now we keep the x squared on the bottom, but let's say now we look at a second function, y2 is root x over x squared. So now if we classify the type of graph, type of function we've got here, what we've really got is it's a root on the top, we've got a polynomial on the bottom. So now which one is going to win? So we look at our growth rates chart, our order of terms, and we can see there that the polynomial is going to grow much faster than the root. So the term on the bottom now gets bigger and bigger and bigger. So if the term on the bottom is getting bigger, then that limit, if we go all the way to x going to infinity, is going to be 0. The bottom term is much bigger. It dominates the term on the top. So we can say now the limit of this function, y2, as x goes to infinity, is now going to be 0. Because again, the term on the bottom grows much faster. Now, a final example of what happens when we have a function on the top that seemingly grows at the same rate as the one on the bottom. This is an interesting problem to think about. So if we have a function y3, and let's suppose this one is 2x squared plus 1 on the top, and then maybe on the bottom we have x squared plus 3x plus 4. So this is a relatively complicated function. We've got a polynomial on top, a quadratic term on the top, divided by another quadratic. But when we're thinking about what happens as x gets bigger and bigger and bigger, we're just again comparing the growth rate of the term on the top and the growth rate of the term on the bottom. But this time, if we follow that approach, what we've got here is the top is a polynomial and the bottom is also a polynomial. So this is not actually going to help us. We have to think a little bit more about how to compare these terms. So in this instance, what we do is we look at the individual pieces of those terms. So when x is really big, if I have the function on top, 2x squared plus 1. So when x is enormously large, the plus 1 doesn't really do anything, right? It just adds 1, but we're already at such a big number that adding 1 just doesn't make a difference to that number. So we can say, well, this is basically 2x squared for large x. And then on the bottom, we've got something similar. So the x squared plus the 3x plus the 4, again, for those really big values of x, right? The 4 doesn't really do much. The x, the 3x term, that's linear. And linear is dominated by, it's beaten by the quadratic, the polynomial term there. So this is actually just going to look like x squared. And we call these the dominant or the leading order terms of that numerator on the top and the denominator on the bottom. And if we just look at those dominant or leading order terms, we can now see what that limit's going to be. So we can say y3 approximately looks like, for large x, 2x squared over x squared. So then those x squareds cancel, and so we can say that it looks like 2 in the limit as x goes to infinity. So there we go. So what have we learnt here? We have looked at growth rates of different functions. We've seen how the smallest or shortest growth rate function is something like a root, and then that's increased towards, no, it's not that. Sorry, let me just do that ending again. As x goes to infinity. As x goes to infinity. Okay, so what have we learned here, right? To summarize what we've been discussing. We compared various different functions and looked at their growth rates, starting from logs, increasing to roots, linear equations, linear graphs, polynomials, and exponentials. And we saw how the steepness, how fast that graph is increasing, is telling you a lot about its growth rate. And then we've ended by comparing different growth rates, and we've got there a little brief introduction to the idea of a limit. This piece of mathematics comes from the year 1202 and a mathematician called Leonardo of Pisa. Leonardo was interested in studying the breeding patterns of rabbits. Now, instead of using rabbits, we will today be using rubber ducks for obvious reasons. Now, the rules of this problem are as follows. If we have an initial single pair of breeding rubber ducks, and then they produce offspring, who themselves can then breed and produce more offspring, we would like to know how many rubber ducks will we have after 12 months, after 1 year. And the rules are as follows. So every time a pair of breeding rubber ducks gives birth, they have offspring, there will be 2 offspring exactly. So every time offspring are produced, we get a pair of offspring. And that pair of offspring will actually have to wait 1 month before they mature, and they themselves are then able to breed and produce offspring. Now, of course, there is a delay between the breeding and the offspring, and that delay is also going to be 1 month. So just to summarize, we have a pair of ducks. They breed. 1 month later, they give birth to 2 offspring, and then it takes a further month before that new pair can themselves breed. Now, it does sound a little complicated. There are a few moving parts, a few things going on. So let's see if I can act this out with some actual rubber ducks. So we begin in month 0, the very beginning of the problem, and we're going to have, according to Leonardo, we have a single pair of non-breeding ducks. So at this stage, they are unable to breed. Let's suppose they are newborns, they've just been born. Now, that's at month 0. 1 month later, they have matured. So they move from being non-breeding into the breeding duck category. And nothing else has happened. So 1 month later, we still have a single pair, but now they have matured and are able to breed. So what that means is another month later, so after 2 months, they have given birth. And again, according to the rules of Leonardo's problem, they have given birth to a pair of rubber ducks, a pair of offspring. So we're now 2 months in, and what we've got is a breeding pair, a single breeding pair, and a single non-breeding pair. Now, here's where it gets a little bit complicated, so we have to be careful. Going to month 3, the non-breeding pair will mature. So by month 3, the non-breeding pair move into the breeding side. But the original pair, well, they continue to breed. So they've now had another pair of offspring. So what that means is that after 3 months in total, we now have 3 pairs of ducks. Okay, let's try a couple more steps. So we've got 1 non-breeding pair, and we have now 2 breeding pairs. So if we go forwards a month, these 2 breeding pairs will each produce a pair of offspring. Those 2 each produce offspring, and the non-breeding pair moves into the breeding pair setup. So we're now in this situation. And we'll do 1 more, so I've got a few more ducks left. So again, 1 month later, all of the non-breeding ducks are going to move across, and at the same time, all of the breeding pairs produce offspring. So I'm going to get 6 new. We have 6 total ducks. So 3 breeding pairs there produces 3 pairs of offspring, and the non-breeding ones move across to here. So this means that after, I believe, 5 months, I think we've got a total of 8 pairs of ducks. And unfortunately, I've run out of ducks. And also, to be honest, it's quite hard to keep track of exactly what is going on here. This is why Leonardo posed this problem. It's quite an interesting one to think about. So I'm going to see if we can do this by drawing a graph. So if we now think about the y-axis, this is going to be the number of pairs of ducks that we have. And then on our x-axis, we're going to have time. So this will be the number of months that have passed. So if we think back to those first few steps, we started with 1. So at month 0, we had a single pair let's mark that here, single pair of non-breeding ducks. So it took them a month to mature. So after month 1, that was 0, after month 1, we're still at 1. But now they could then themselves have offspring, and we saw that after month 2, we'd now gone up to 2 up here. And I'll try my best to draw this as much to scale as I can. Then after 3 months, we saw that now we actually ended up with 3 pairs. So we were kind of like here, 3, sort of like this. Okay, so there's kind of some kind of like possible straight line linear relationship happening. But then after 4 months, it didn't just go up to 4. We saw that it went up to 5, didn't it? So that's like up here now. So after 4 months, we kind of gone up a bit more to like here. And then after 5 months, we ended up with 8 pairs of ducks, right? So this is definitely not linear anymore. So after 5 months, we're now like, I've kind of run out of space here, but it's going to be something up here, sort of shooting off the board, going right up to 8. So if I sort of try and think about the shape of this, this is hopefully looking, it kind of looks like an exponential growth pattern. We're seeing here the breeding patterns of our rubber ducks is actually an exponential graph. And in fact, the base of this exponential, so when we talk about an exponential graph as being y equals a to the x, we talk about a as the base. And the base here is actually a is equal to 1.618 ... which some of you may recognize as the famous golden ratio. So the breeding patterns of our rubber ducks are actually an exponential graph, an exponential relationship following the golden ratio, which is pretty magic, if you ask me. Now, once we've established this pattern and this graph, we can now use this to try and figure out the answer to the question. But there's actually a slightly easier way, because if we think about the numbers that I've written out here and drawn the points of, and some of you, again, may have spotted this. We went 1, 1, 2, 3, 5, 8. And then that pattern would continue. And what we're seeing here, this is a very famous sequence of numbers. And very well done if you got it. We've got 1, 1, 2, 3, 5, 8, also known as the Fibonacci numbers. So Leonardo of Pisa, his nickname was Fibonacci. And these were the numbers that he came up with, and he came up with them by thinking about breeding patterns of rabbits, or here, rubber ducks for us. And the way that the Fibonacci numbers work is you start with the first 2, so it goes 1, 1, and you start with those numbers, and then you get the next one by adding them together. So 1 plus 1 gives you 2, 2 plus 1 gives you 3, 3 plus 2 gives you 5, 5 plus 3 gives you 8. So the next number would be 5 plus 8 would give us 13. So now, without even playing around with ducks, we know that after month 6, we just get the next number in the Fibonacci sequence, which is going to be 13. And we know that these numbers are going to explode. They are increasing according to this exponential curve, this exponential graph. And so after 12 months, the number is going to be really, really big. So big, in fact, that I'm going to need protection, I think. So after 12 months, the total number of ducks is 233. In this chapter, we've seen how graphs can be used to visualize problems, whether mapping out... Nope, not that. Displaying a map. OK. Sorry, I'll go again. In this chapter. In this chapter, we've seen how graphs can be used to visualize problems, whether... If I say mapping out a map, go again. In this chapter. In this chapter, we've seen how graphs can be used to visualize problems. Sorry, give me 10 seconds. I think I just need to walk. In this chapter, we've seen how graphs can be used to visualize problems, whether displaying a map or showing a linear relationship between variables. We also looked at some real-world data and the need for non-linear graphs. We saw quadratics, polynomials, and exponentials. We then also looked at the graphs of inverse functions in the form of the square root and the logarithm function, which we found by reflecting in the line y equals x. And finally, we finished by comparing the different growth rates of those graphs, and we also calculated the growth rate of the breeding patterns of rubber ducks and saw not only was it exponential, but also felt... It was good until the last sentence. Oh, sorry, I'm just tired. In this chapter, we've seen how graphs can be used to visualize problems. In this chapter, we've seen how graphs can be used to visualize problems, whether displaying a treasure map or showing a linear relationship between variables. We also looked at some real-world data which saw the need for nonlinear graphs and relationships in the form of quadratics, polynomials, and also exponentials. We then reflected those graphs to get the inverse graphs in the form of square roots and logarithms. We then compared the growth rates of all of the graphs that we'd been discovering. In this chapter, we've seen how graphs can be used to visualize problems, whether displaying a map for finding treasure or showing a linear relationship between variables. We also looked at some real-world data examples and saw the need for nonlinear graphs in the form of quadratics and exponentials. We then saw the inverses of those graphs by reflecting in the line y equals x, and we compared the growth rates of all of the different graphs that we'd introduced. We ended by looking at the breeding patterns of rubber ducks and discovered not only is it an exponential graph, but the growth rate is equal to the golden ratio. Next time, we'll take a deeper look at exponentials and also solve some fun estimation problems.